Today we're going to talk about the kinetic energy of rotation. Here's again our chart showing the kind of correspondence between linear and rotational motion. And today we're going to talk about kinetic energy, work, and power. And you can see that there is kinetic energy and work and power involved when we're moving something in some linear direction, but there's also energy and power and work involved with making something rotate. So let's figure out how much kinetic energy a ring has when it rotates. Well, kinetic energy is 1/2 mv squared. So if I have this ring rotating about its axis of symmetry, the kinetic energy is just going to be 1/2 mv squared. Well, I could break my ring up into little pieces and find the linear velocity of each little piece. But in this case, each piece of my ring has the same magnitude of velocity, and that velocity is just r squared times omega squared. Sorry, the velocity is r times omega, so v squared is just r squared times angular velocity squared. But, of course, mr squared is just the moment of inertia for our ring, so I can write the rotational kinetic energy of the ring as 1/2 I omega squared. And you can see that's very analogous to the linear kinetic energy, 1/2 mv squared, because I plays the role of m when we do rotations, and angular velocity plays the role of velocity, so you ought to have no difficulty remembering that the kinetic energy due to rotation is just 1/2 I omega squared. What if I have something more complicated, something that's not just a ring, where different parts of the object are moving at different linear velocities? Well, what we can do is we can say, well, the total kinetic energy is just the sum of the kinetic energies of the different pieces. All right, and so I'm going to take this disk, for example, and break it up into rings. And each one of those rings has a little kinetic energy, which is 1/2 v squared times the little bit of mass in that ring, which is, of course, 1/2, right? The velocity, the linear velocity is just radius times omega, r times the angular velocity. So the little bit of kinetic energy in this ring is 1/2 r squared omega squared times the little bit of mass dm. And of course, the mass is just, the little bit of mass is just the density times the little bit of volume in this ring. So now I just take that and I integrate that to find the total kinetic energy due to the rotation of this disk. And I realize, oh, the 1/2 and the omega squared come out, they're constants, and then I'm just left with the integral of r squared rho dv, but that's precisely the integral we do to find the moment of inertia. So that means that the rotational kinetic energy of this disk is just 1/2 omega squared times I. And it turns out that's a general property. The kinetic energy stored in something because it's rotating is equal to 1/2 I omega squared. Now, if I have an object that's rotating and translating, right? So imagine, I throw a frisbee, it's spinning, but it's also moving, then the total kinetic energy is the linear kinetic energy plus the rotational kinetic energy. So it's equal to 1/2 mv squared, where v is the velocity of the center of mass, how the object as a whole is moving, plus 1/2 I omega squared. And so the main takeaway for today is that the kinetic energy due to something rotating is 1/2 I omega squared. So make sure you remember that. That's the main takeaway from today's video. So let's use that to try and solve a problem. A marble, a cylinder, and a thin-walled ring, each with a diameter of 1 centimeter and a mass of 1.8 grams, roll down a ramp which is 1 meter long and which is at an angle of 20 degrees with respect to the horizontal. If they all start at the top of the ramp with no velocity, what will their velocity be when they reach the bottom? Well, we've done problems like this before, only with like blocks that are sliding without friction. It's the same idea. We're going to use conservation of energy. So energy initial equals energy final. The initial energy is just the potential energy that they start with, which is mgl sine theta, all right, where L is the length of our ramp and theta is the angle of the ramp. relative to horizontal. So this is just mg times the initial height of the objects before they roll down the ramp. Well, the final energy, there's going to be no potential energy when they get to the bottom, because that's where we've defined y to be 0. So it'll just be the kinetic energy, which is the sum of the linear and the rotational kinetic energy, which is 1/2 mv squared plus 1/2 I omega squared. So now we can just set the initial and final energies equal to each other. Oh, sorry, I'm getting ahead of myself. So remember, omega is just, so V is omega times R, so omega is V divided by R. So the velocity of the outer edge of something rotating is related, as you'll recall, to the angular velocity. And so we want to write everything in terms of V because we know they're related, and then we can just solve for V. So we'll set initial energy equal to final energy, and now I'm going to factor out the v squared, and I look and I say, oh, this is just something with a bunch of things that were given times v squared, and so we can solve this equation for v, and there's our answer. So now I just need to plug in the moment of inertia for each of these different shapes. So for the thin ring, the moment of inertia is just mr squared. I plug that into the equation, and the mr squared cancels with the mr squared, and we get the square root of gl sine theta. So remember, for a block sliding without friction, the velocity we would have gotten is the square root of 2 gl sine theta. So the thin ring will be going a factor of root 2 slower than if it just slid down the ramp. And that makes sense because we have put some of the kinetic energy into the rotational kinetic energy, which means there's less energy left over for translational kinetic energy, so you expect it to be going at a slower velocity. All right, what about the cylinder? The moment of inertia for a cylinder rotating about its axis of symmetry is 1/2 mr squared. So we plug that into our formula for the velocity, and when we solve that, we get the square root of 4/3 gl sine of theta. So 4/3 is bigger than 1. So it looks like the cylinder is going to be going faster than the ring. And that makes sense because the ring has more of its mass concentrated further from the axis of rotation. That means more of its energy will be rotational kinetic energy rather than translation. The cylinder has less mass concentrated far away from the axis, so less of its kinetic energy will be rotational kinetic energy. Now, finally, the sphere. The sphere has a moment of inertia of 2/5 mr squared. So we plug that into our formula, and we find that the velocity of the sphere is the square root of 10/7 gl sine theta, which is even larger, even closer to the sliding velocity. And that makes sense because a sphere has even less mass concentrated far from the axis and more mass concentrated near the axis of rotation when compared to a cylinder. So the winner is the sphere, coming in at 2.19 meters per second. In second place is the cylinder, and in third place is the ring. And for comparison, if it had been just a block sliding without friction, this is what the velocity would have been. And so hopefully this makes sense. The ring has the most mass concentrated further from the axis of rotation, and the sphere has more mass concentrated close to the axis of rotation. So that means less of the final kinetic energy will be rotational energy, meaning there's more energy left over for translation. And then, of course, something sliding without friction doesn't have any rotational kinetic energy. All of the gravitational potential energy is converted to linear kinetic energy, so it goes the fastest. All right, so we understand kinetic energy. What about work? Well, work is the change in kinetic energy, but work is also the integral of force times distance. Well, let's once again look at a ring and imagine that I'm pushing on the ring to get it to speed up. All right, so the dot product here says that work is just the component of force in the direction that I'm moving the thing, which would be the theta component of force, the component of force tangent to the rotation of my ring. Well, if I'll note that a little bit of motion, ds, that's just a little bit of arc, So that's just r times d theta. So I'm going to write ds as r times d theta. But notice the tangential force times r, that's just the torque that I'm applying. So this is just torque d theta. And so there's my formula for work. Now, power is just work per unit time. So let's take a little bit of work. All right, a little bit of work is torque times a little rotation. If power is just the derivative of work with respect to time. So if I just take my little bit of work and divide by dt, I'm going to get tau dotted into d theta dt, which is angular velocity. So if we look at this chart here, linear kinetic energy is 1/2 mv squared. Rotational is just 1/2 I omega squared, right? I just replace m with I and v with omega, and I get rotational. Work, for linear work, I integrate force times distance. For rotational motion, I just replace force with torque. I replace x with theta, and I get the equation for the work done as I make something spin. And then power, right? We found for linear motion, power is force times velocity. Well, for rotational motion, I just replace force with torque, replace velocity with linear velocity. And so hopefully you can remember all these relations. There's not a lot of new equations then to really learn to do rotational motion. Okay, so let's consider this. You're testing how freely the wheels on your bike spin. So you flip your bike over such that the wheels are up. Then over a period of 3 seconds, you push on the front tire, getting it to spin at a rate of 1.5 revolutions per second. If the moment of inertia for the wheel is 0.75 kilograms meters squared, what is the average force and torque on the wheel over the 3 seconds? Well, force is mass times acceleration, right? And so the average force is just the mass times the average acceleration. And the average acceleration is change in velocity divided by the time that's passed. But of course, in this case, the wheel does not move. It spins, but it does not translate. It's stuck to the axle. So that means the average force we put on the wheel is 0. Well, the force we put on the wheel isn't 0, but the axis is keeping the wheel from moving. We push on it with a force, the axis pushes in the opposite direction. So the average net force on the wheel is 0. But what about the torque? Torque is I times alpha, right? This is just F equals ma, but converted to the angular version. Well, that means the average torque is the moment of inertia times the average angular acceleration. And the average angular acceleration is change in angular velocity divided by the time it took to make the change. Well, the change in linear and angular velocity is just, right, we started with no angular velocity, so it's just the final angular velocity, which is 1.5 times 2 pi radians per second, right? It does 1.5 rotations per second, and there's 2 pi radians in every rotation. The moment of inertia is given, and the time is given, so we can just plug that in and find that the average torque is 2.36 Newton meters. Now, just as a side note, a Newton meter is also known as a joule, but it's weird to talk about a torque in terms of energy because torque is more closely related to force. So usually when we talk about torques, we'll give the units as Newton meters. All right. All right, now here's the same problem, but now we want to know how much work we did on the wheel as we spun it up. But remember, work is changing kinetic energy, and the kinetic energy is 1/2 I omega squared, and there's no initial kinetic energy because it's not moving, so the change in kinetic energy is just the final kinetic energy, which is 1/2 I angular velocity squared. And so we just plug the numbers in, and we get our answer, 33.3 joules. All right, now because work is an energy, we don't call it Newton meters, we call it joules, even though we know technically they're the same thing. All right, we can also calculate work by integrating torque d theta. And I just want to show that we get the same answer when we do that. So the average torque times d theta ought to be the work that we do. All right? So the change in theta is just, we use our equations of constant acceleration. Now the tire is not accelerating at a constant rate. Necessarily. We didn't really say how it's accelerating. We're whacking it with our hand. But we know that the energy that we put in is the same, right? The energy we put in only depends on the final angular velocity. So I can calculate the work done by pretending it was constant acceleration because I know I'll get the same result. So let's just use the equation of constant angular acceleration. The initial angular velocity is 0, so this is just 1/2 alpha t squared, but angular acceleration is just torque divided by moment of inertia. And so the work then is just this right here. And right, we just take this d theta, plug it into here, and we get this. And then recall that the average torque that we found earlier is I delta omega over delta t, and we plug those all in, and it turns out we get exactly the same equation. The work done is 1/2 I delta omega squared. All right, so it all works out. Everything's kosher. And now we're going to do the same problem, but now we're going to find the average power we put into the wheel over 3 seconds. Well, power is the derivative of work with respect to time. So the average power is the work done divided by the time it took to do it. And we know the work done. We already calculated that. And so there is our answer, an average power of 11.1 watts. All right, so I'm just going to leave you again with this chart. Today we talked about kinetic energy, work, and power, and we found that rotational kinetic energy was very, it's the same thing as linear. It is linear kinetic energy, but it's the linear kinetic energy of the little pieces of the object that's spinning. So we can break the kinetic energy up into a linear piece, where the velocity is just kind of the average velocity of the big chunk of stuff that's moving, and then a rotational piece that has to do with the angular motion of our object. And the equation is very analogous to the linear kinetic energy equation. We just replace mass with linear momentum, or moment of inertia, and replace velocity with angular velocity. And then we came up with an integral to find work. Work is change in kinetic energy, and we can find it by doing an integral. And just like with kinetic energy, we take the equation for linear work and we replace force with torque and x with theta. We just replace the linear variables with rotational ones. Same thing with power. So the power we give something as we spin it up or slow its rotation down is just torque times angular velocity. And next time we'll talk about our remaining piece of the puzzle, which is rotational momentum or angular momentum.